To put into perspective how enormous our solar system is, you could line up about 350,000 Earths between Sun and Neptune, the farthest planet. Yet, despite being separated by hundreds of millions of kilometers in space, these planets have a massive effect on the climate here on Earth. They drive the ice age cycles and cover almost half of the area of our planet in vast and thick glaciers. It might sound like it is straight out of science fiction, but it's not. This freezing was so intense that 21,000 years ago, all of today's Canada lay buried beneath a 4-kilometer thick ice sheet. The land where New York City currently stands was covered by half a kilometer of ice. Down south, 1.5 kilometer thick ice sheets covered half of Chile and Argentina. Across the Atlantic, entire northern Europe and vast stretches of Russia were frozen under towering ice sheets. How can these worlds so distant, orbiting the sun in far reaches of space, shape the fate of our own world we call Earth? Let's dive in. First things first, how do we know of these ice-covered periods that have occurred long before human civilization even began? This story starts with some clues that these massive ice sheets left scattered all over Earth. This huge boulder is called Okotoks, meaning big rock. It sits isolated on the vast flat plains of Alberta, Canada, right here. Now, here is what's strange about this rock. It is a piece of Mount Edith Cavell located nearly 400 kilometers away in the Rocky Mountains, right here. Now, how this rock got so far from its source stumped geologists. Some said it was carried here by water, some said it was ejected by a volcano. But this rock showed no signs of erosion or rounding, ruling out the water theory. Its composition doesn't match any of the local volcanic material, ruling out the volcano theory. How this rock got so far with almost no damage remained a mystery for a long time, until geologists conclusively established that this 15,000-ton rock was plugged from the mountainside and was carried here 400 kilometers far like a pebble on a conveyor belt by a massive ice sheet that once covered most of Canada. When that ice sheet finally melted, the big rock was gently laid down, here where it still stands today. Thousands of kilometers away, in the Jura Mountains of Switzerland, geologists found polished rock faces nearly 1 kilometer high up on the mountain slopes, carved smooth, possible only by an immense force. Massive ice sheets that once covered entire valleys and even possibly overflowed the Alps. Just a reminder, the average elevation of Alps is 2.5 kilometers. These clues left behind by the ice sheet from the plains of Canada to the peaks of Europe proved that Earth had witnessed periods when huge ice sheets extended far beyond poles into our continents, unlike today when they are confined majorly to Greenland and Antarctica. But why was this freezing happening on Earth? For decades, scientists and paleoclimatologists tried to build a climate model that could explain what caused these vast ice sheets. As evidence of these ice-covered periods piled up, the scientists zoomed out from the individual clues and looked at the bigger picture these clues painted, and noticed something peculiar. The timings of these freezing periods weren't random. There was a pattern. The ice cover reached its peak roughly once every 1 lakh years, like clockwork. And this clockwork had two main settings: a cold and long 80,000-year glacial phase, when ice advanced from the poles towards the equator, followed by a relatively warm and short 20,000-year interglacial phase, when ice retreated towards poles. Earth has been alternating between glacial and interglacial phases. But this regularity posed a huge problem for climate models that relied on Earth's internal systems as a cause. You see, Earth's internal temperature regulation systems like ocean currents, greenhouse gases and volcanoes are incredibly complex and frankly a little chaotic and cannot produce such stable, predictable and long-term temperature cycles on their own, The cause had to be external. So scientists looked away from Earth and into space for an answer. And they found it. Written not in Earth's oceans or atmosphere, but in the geometry of our solar system. Let's quickly go over what you already know from school. Earth spins on its axis, giving us day and night. Earth orbits around the sun, giving us an year. This orbit of Earth around the sun isn't a perfect circle, but a slight ellipse. And this axis is tilted at 23.5 degrees with respect to the orbital plane, giving Earth its seasons. Simple enough, right? Let us keep these aside, we'll need them in a moment. In the 1600s, Newton developed his gravitational theory, which in essence said every object in this universe attracts every other object. Building on this theory, in the late 1700s, mathematicians Joseph Louis Lagrange and Pierre Simon Laplace calculated how much effect various planets of our solar system have on Earth and Earth's orbit. They summarized these effects into the secular perturbation theory, in which they noted that 3 planets in particular, Venus and Mars, the planets adjacent to Earth, and Jupiter, the most massive of our solar system, have the largest influence on Earth. At certain specific times in their paths around the Sun, these planets align perfectly, pulling Earth in one direction, causing Earth's orbit to elongate, increase eccentricity of Earth's orbit around the Sun, and at other times, neutralize each other's pull due to their relative positions, causing least eccentricity in Earth's orbit. Derived from this, here are 4 things that you may have missed or probably weren't taught in school. The direction in which the axis of rotation of Earth points to wobbles slowly, somewhat like a spinning top, a phenomenon called axial precession. The elliptical shape of Earth's orbit isn't constant. It stretches and shrinks, gradually changing from almost circular to more elliptical and back again. Even the entire elliptical orbit of Earth around the Sun slowly rotates in space, a phenomenon called apsidal precession. The tilt of Earth with respect to orbital plane, called obliquity, isn't fixed at 23.5 degrees, but gradually oscillates between 22.1 and 24.5 degrees. These aren't daily changes, but play out over tens of thousands of years. Axial and apsidal precession, when combined, have a periodicity of 23,000 years. This affects when seasons on Earth occur relative to Earth's position around the Sun. That is, at which position of Earth in its orbit do we experience summer and winter. Eccentricity has a periodicity of 1 lakh years. This subtly alters how much solar energy we receive overall and also the length of seasons. Obliquity has a periodicity of 41,000 years and affects intensity of seasons on Earth. A smaller tilt makes seasons both summer and winter milder, and a greater tilt exaggerates seasons. Hotter summers, colder winters. The combined effect of these 3 factors, eccentricity, obliquity, and precession, determine how extreme or mild the summers and winters on Earth are. By the early 1900s, many scientists had already predicted that this interplay among the 3 factors, eccentricity, obliquity, and precession, is the missing link that is driving these long-term climate shifts and causing the ice covers. But the mathematics required to prove it was brutally complex for the time. Until a Serbian mathematician and engineer, Milutin Milankovitch, decided to take on the challenge. He built his theory around the key hypothesis that if summers at high latitudes are just warm enough that the snow from the previous winter doesn't completely melt, that snow sticks around. And in the next winter, more snow piles on top. Over tens of thousands of years, this snow compacts into what we call ice sheets. With his deep knowledge of orbital mechanics, Earth's geometry, and climatology, Milankovitch undertook the monumental task of calculating how much solar energy per unit area, or insolation, reached every latitude of Earth during every season across hundreds of thousands of years as Earth's distance, angle, and orientation with respect to Sun, that is, eccentricity, obliquity, and precession, changed. His math showed that the historically recorded ice sheets appeared when these 3 cycles lined up in just the right way and caused lowest sunshine in summer in the north high latitudes. In 1941, Milankovitch published this incredible work in his book Canon of Insulation and the Ice Age Problem. His work was so ahead of its time that it took technology 3.5 decades to finally catch up and provide the definitive proof. And this proof was hiding in a place no one had imagined, at the depths of the oceans. Our universe has two kinds of oxygens, O16, the regular one, and O18, the heavier one. In extension, Earth's oceans also have two kinds of water molecules. The water molecule with O16 in its H2O and the water molecule with O18 in its H2O. Now, these two molecules differ in a lot of ways, but the one of interest to us in this context is their difference in rate of evaporation. Because the H2O18 variant is heavier, it evaporates slower when compared to the H2O16. When Earth's average temperature is low, the evaporated water forms ice caps and doesn't return to the ocean. Because H2O18 is slow at evaporation, it gets left behind in the oceans. As a result, H2O18 concentration in the oceans increases and H2O16 concentration in the ice sheets increases. When the Earth's average temperature increases, these ice sheets with high concentration of H2O16 melt and return the H2O16 to the oceans, making the H2O18 concentration in the oceans lower. In essence, the H2O18 concentration of ocean of a time can tell us how big the ice sheets on Earth were at that particular time. But do we have the historical record of H2O18? Fortunately, yes. But not in a dusty old library book, but in the corpses of this tiny organism called Foraminifera that lives at the bottom of the ocean. You see, when a Foraminifera makes its shell, it uses the water that surrounds it, the ocean water. So, the shell of a Foraminifera can tell us the H2O18 concentration of the ocean when it lived. When this organism dies, the shell doesn't decompose. It sinks to the bottom of the ocean and becomes the ocean floor. So, layers upon layers of these shells belonging to different time periods of Earth sit stacked at the bottom of the ocean and hold the record to the ice volumes and thereby temperatures on Earth that existed when that layer was formed. In 1976, a team of 3 scientists experimented on these deep sea sediment cores and reconstructed the volumes of ice Earth contained at various points in time in the last 1 million years. And there was the proof. The times when Earth contained highest volumes of ice according to these experiments perfectly matched with the times when Milankovitch's calculations showed lowest insulation values at high latitudes. Peak ice volumes can be clearly seen at 1,41,000 and 23,000 years, corresponding to eccentricity, obliquity, and precession. The theory wasn't just elegant anymore, it was proven. It was conclusively established that in this grand cosmic ballet of sun and its planets, the tiny tugs and pulls between the planets can determine the temperature and climate here on Earth, which is millions of kilometers away. These external factors, when combined with internal factors like albedo, ocean circulation, and greenhouse gases, drive the ice age cycles which are recorded in our climate history. And this is precisely why Earth was covered with thick layers of glaciers 21,000 years ago. All this is fascinating, but what does it mean for us? So, let me zoom out to show you the big picture and ask you a question that might surprise you. Are we in an ice age? Well, if we go by the scientific definition, an ice age is a period when Earth has sustained ice caps at its poles. And we do have ice caps at our poles in Greenland and Antarctica. So, technically, we are in an ice age. More specifically, we are in the warmer interglacial period of a much larger ice age. So you must be thinking, what is the big deal about ice ages? That is why you must know what happens at these peaks to appreciate what you have at these dips. For starters, at these peaks called greenhouse periods, the opposite of ice ages, the average temperature on Earth would be at least 10 degrees higher. The water that was drawn from the oceans and held at the poles by the ice caps gets dumped back into the oceans, raising the sea levels by 150 meters and submerging entire coastlines and islands that we know. Not a pretty picture, is it? And one last thing, the glacial and interglacial cycles that we have been discussing are just oscillations within this ongoing ice age, the fifth major ice age that planet Earth is experiencing in its 4.5 billion year long history, called the Late Cenozoic Ice Age, which began 34 million years ago. In this ice age, the last glacial period ended 21,000 years ago, and currently we are in the interglacial period. The first four ice ages each have had different triggers. What I mean to say is there were much grander events happening on Earth that played a major role in causing these ice ages than the cosmic factors. You will get to hear these amazing stories in episode 6 of this series, so stay tuned. Thank you for watching. Until next time, keep asking why.